Hello everyone, my name is Haoye Wang. I'm from Zhejiang University. My topic today is context-aware retrieval-based deep commit message generation. Version control systems are widely used to manage changes between versions. When submitting a code change, developers can attach a commit message to describe the change and explain why the change was made. And we refer the code change here as diff. This commit message is recorded in the version control system, contain the contents and intentions of these code changes, and can provide the information needed to understand the software evolution, like software problems, future additions, defect reports. Therefore, it plays a very important role in software development maintenance. Unfortunately, developers often cannot actually describe the code changes in natural language. The income lags behind, which cannot be reflected in writing. Moreover, as the structure of software repositories becomes complex, it becomes difficult for developers to write high-quality commit message. They often ignore the writing of the commit message. Thus, it is necessary and helpful to automatically generate a commit message for code changes. Several approaches have been proposed to generate commit message automatically. This method can be roughly divided into three categories. The first one is rule-based method. This kind of approaches mainly use predefined rules and templates to generate a commit message, like do Y instead of Z. But this kind of method cannot cover all the cases or explain the reasons or purpose behind the code changes. And in the face of massive data, its labor consumption is terrible. The retrieval-based approaches utilize information retrieval to reuse the commit message of similar code changes. However, there are high requirements for the coverage of datasets. It is difficult to adjust the generated results according to specific conditions. Learning-based approaches have the ability to learn the semantic correspondence between source code and the commit message, and have achieved promising results. They have become a trend to solve the commit message generation problem. But there are still two problems. They prefer high-frequency words in the corpus, and their generated messages are relatively less readable. If a ground truth word is raw in the training corpus, this kind of methods may generate a wrong result. In learning-based methods, an addition problem exists, which we call exposure bias. Most MIT methods are typically trained with teacher forcing, in which the model generates each word conditioned on the ground truth word of the target sequence. Specifically, at training time, the ground truth word is passed as the next input to the decoder, while at the testing time, the gold target sequence is not available. Mm. So the previous word predicted is fed as context. That is, the MNT model is never trained to learn how to predict under the condition it may match at a meeting phase. We present two examples to explain the motivation. The first example is about the low-frequency word problem. The commit message generated by a typical retrieval-based method contains a low-frequency word side only. The MNT-based method ignores the ground truth word, which tend to generate high-frequency words like missing and in. If we use retrieval similar commits to guide the learning-based commit message generation, it may better take into account both high-frequency and low-frequency words. The second example is about exposure bias. At training time, even if the first word actually generated is fixed, the model still uses a ground truth word 10 as context when predicting the second word. However, in this case, the model is trained to predict off conditioned on the previous word 10. While at testing time, once the model predicts a wrong word fix, the wrong word has to be fed as context because there is no guide from truth. So the errors accumulate among the sequence and cause the quality of generated sentence to decrease. We propose an approach named correct to address these two limitations. First, let's see the training model. Most MNT models use a ground truth sequence as the input of the decoder. But in the testing phase, the commit message is generated according to the previous words. To address this gap, in the training phase, we adapt a privacy-induced decay sampling mechanism. The decay sampling will randomly select the previous output of decoder or the ground truth vector as context to make the model gradually aware of previous alignment choice. At the beginning of the training phase, the model selects the embedding vectors of ground truth word as context at a greater probability. As the model converges gradually, the previous output of the decoder which contains the information of previous alignment choices are more frequently chosen as context. This setting makes our training process gradually change from fully teacher forcing to a less guided scheme. After obtaining the trained model, we need to generate commit message given a test diff. We use the diff retrieval module to retrieve relevant commits from the training set, given a diff from the validation or test set. In order to improve the performance for predicting low-frequency words, we incorporate in the knowledge of similar commits from the training set to guide the commit message generation. Given a diff for testing, we reuse the trained model to represent the given diff as a semantic vector and retrieve the most similar diff in the training set. While generating each word, correct decodes each retrieval diff and use the retrieval information to adjust the final probability distribution of all the words in the target vocabulary. In this way, Karak is able to incorporate the advantage of retrieval-based methods and thereby improve the quality of the final generated messages. Next, we introduce the data preparation. Jiang published a dataset for commit message generation. However, they only collect top 1,000 Java projects from GitHub. In order to evaluate the performance of Correct on a large-scale dataset, we collect the top 10,000 repositories, which were created between January 2012 and December 2018 on GitHub. We carefully cleaned and processed the dataset using keywords in combination with patterns to filter out as much noise as possible. We choose NGN and PTR, and CMSG as our baselines. PTR, and CMSG is an attentional encoder-decoder module combined with pointer generator network. This method also directly translates diff into a commit message. NGN method mainly uses nearest neighbor algorithm to retrieve the top K code change from the training set. Our first research question is, How does Coric perform compared to other baselines? The authors of PTRG and CMSG conducted their experiments and demonstrated good results on the dataset from John without removing noisy messages. However, Zhongxin Liu have reported that if we remove these noisy messages, which have little information or can be automatically produced by some rule-based tools, the performance of NNT will decrease a lot. Our experimental results confirm the results once again when these noisy messages are removed from our dataset. And we can see from the table that our approach achieves the best performance of our evaluation metrics, and the other methods perform better on top 10,000 dataset. This shows the advantage of our large-scale dataset. The second research question is what impact each of our main components have in our model. We have two main components in our model, the retrieval component and the case sampling component. In the table, the basic model refers to the model remove both components. Retrieval refers to the similar diff retrieval module in our model. From the table, we can see our retrieval model performance is better than NGN on both datasets. Both variants that remove one single component outperform the basic model, and Coric can still be further improved when combining both the main modules. We perform experiment on the two data mentioned above to show that the commit messages generated by our model contain more low-frequency words. We compare our model with the original attentional encoder-decoder model and perform word in frequency statistic analysis on the generated messages. First, we collect all the words in the generated messages. In order to determine the probability of these words appearing in the entire corpus, we take the number of times these words appear in the training set as their frequency. Since we are focusing on low-frequency vocabulary, then we divide these frequencies into 7 groups, shown in the table. But please note that we do not claim that all the frequency words added are the correct generated word. To further check whether Coric can generate low-frequency words correctly for the test commit, we run our model on the dataset where each commits have low-frequency words in the reference message. The dataset is the low-frequency 10,000 dataset in the table. From the table, we can see that the Coric performs better than the basic model on both low-frequency 1,000 and low-frequency 10,000 datasets. These results show that the Coric can address the low-frequency word problem while generating commit messages. And we also investigate the effect of our model on exposure bias. We can see there are more correct words in the commit message generated by the decay sampling mechanism, and as indicated by the improvement of 1 gram, 2 gram, 4 gram, 3 gram, and 4 grams score, the decay sampling mechanism does reduce the probability of word errors in the generated commit message by making model aware of the previous alignment choice. It indicates that there are more ground truth words in the commit message generated by approach with decay sampling mechanism. Evaluation metrics we used in the experiments above calculate the textual similarity between reference and generated messages. However, since the generated messages is not always perfect. We need to conduct a human evaluation to further evaluate Correc's usefulness in practice. We ask participants to score the full commit message from three aspects, uh, like relevance, usefulness, and content adequacy. The mean score of reference commit messages are 4.2, 3.9, and 3.7 respectively. This indicates that the quality of some developers' commit message still need to be improved. And we can see that compared to the baselines, Correct achieves the best performance in all three aspects. In the discussion section, we discuss the impact of the noisy dataset and the inter-project performance of Correct. You can see that part in our paper. And as a conclusion, in this paper, we proposed Correct, which is the first work that combines the advantage of retrieval-based and learning-based method for commit message generation. The proposed approach is capable of mitigating exposure bias and low-frequency word, and we provide a large news and cleaned benchmark dataset extracted from 10,000 GitHub repositories and make it publicly available. In the future, we plan to incorporate additional information like bug reports and code structure information to further improve automated commit message generation. Thank you. That's all.